definitions are the raw materials of mathematics. Right? If we start with good raw materials, then chances are we're going to make good stuff. It reminds me of Iron Chef, if anyone's ever watched those kinds of shows, right? And I love Iron Chef, especially the old Japanese versions. It's like, awesome. But they'll always say, like in the tasting version at the end of Iron Chef, like, oh, this is delicious because it really honors the ingredients, right? The ingredients they bring to the show are these multi-million-dollar like plates of like raw caviar and sushi and all this stuff. So the best ingredients make the best dishes, right? And so same thing with our definitions, that if we have a really precise definition of something that we all, as a group in this class, but also as a mathematical community more generally, agree is defining what we want it to define, if we're all speaking the same language, that's a prerequisite for us getting to where we need to go with proof. Right? So the step one is having these definitions at your fingertips. I'm not a big advocate of memorization in a lot of classes, especially in classes that require a lot of higher order thinking. But situations arise in any class where if you don't have the basic raw materials memorized and at your fingertips, and if you can recall them accurately, then it's really hard to get to the right place in a proof, because you're starting from spoiled milk and rotten eggs in your ingredients, right? So what I want to do real quick is to take a look at a few of the definitions that I saw walking around on your papers. And we'll just look at them together and figure out if they have all the elements that we need them to have, or if not, then what are some of the ways that we could rearrange them in ways that will make the definition more aligned with what we intend it to be. So let's look at this one real quickly first here. So a set E is said to be dense in R if what you see in this definition, and I'm going to read this definition by translating the symbols into words. I asked you to use symbols, but let's also look at this in words. So a set E is said to be dense in R if, for all A and B, there exists an x in the real numbers such that x is between A and B. So somebody tell me something that works well with the definition that's written down here. One of the strengths of this definition is that it begins with this universal claim, for all A and B. And that is a part of the definition of density that is important. It's important to lead with, right? The first thing about the density of a set is that we make a claim that must be true for all A and B. Okay, another thing that we want to keep is this conclusion. X is in between A and B. So if we just look at that first claim and this last claim, it translates really well to what we often think of as our colloquial understanding of denseness. For all A and B, there is an x such that x is between A and B. And I would say that another thing that works well in the definition as written here is the claim about how many x's must there be. How many x's do we know exist between A and B according to the definition that's written here?
At least one.
At least one, because there's another quantifier being used right here. So for all A and B, there's at least one x in between A and B. So those things in this definition are working really well. They capture our intuitive sense of what density of a set within the real numbers means. So what's not quite there yet on this definition? What might we want to tweak or to refine, or what's not the same as what you have written down? One thing for us to look at here is that when this x is brought to the table, first of all, one thing that's nice is that we've said in this definition what set x should belong to, so where we're getting this x from, right? But in the definition of denseness of a set E, one of the clues to maybe not being quite there on your definition yet is if the rest of your definition doesn't reference the set E, then it's probably missing something. So E needs to play some role in this definition down here. And right now it doesn't. And so, Tori, what you said was that the x that we choose here, we want to be an element of E rather than an element of R. So that's one thing that I would adjust in what's written here. So that now makes it clear that for all A and B, there's at least one element of E in between A and B, right? Not an element of the real numbers. Okay, is there anything else that we should clarify about this definition?
Where A and B are coming from?
That's another thing, right? Is that anytime we introduce the reader to a new element or a new object on the mathematical stage, if you like, we should say where that element is coming from. Right? And that leaves it unambiguous to the reader about the different roles that are being played in this definition between the real set of real numbers on the one hand and the set E, which is being defined to be dense on the other hand. And so where should this A and B be coming from?
Real numbers.
The A and B should be coming from the reals. So anytime we introduce the reader to a new person, we should tell them something about that new person, right? You don't go to a party and make introductions and then just run away. Usually when you introduce somebody at a party, you tell them at least one little thing about themselves so that it'll start the conversation off, right? So that's kind of what we're doing here. Isn't it enough for us to leave this piece out, given that there is a belonging to the real numbers sitting right here? So there's the question of, let's try and rephrase the statement that's written. If we imagine that this part here belonging to R, if we imagine that that doesn't exist, and we imagine that this belonging to R applies to everything that comes before it, this would say, for all A and B in the reals, and for at least one X in the reals, X is between A and B. And again, that might work if A, B, and X were all coming from the same set. But the fact is that in the definition that we want, the X should come from the set E, and the A and B need to be arbitrary elements of the reals. So since they're coming from different sets, we really should specify that separately. Right? So if I'm a proof writer, and this is what we're going to talk about next, if I'm a proof writer trying to write a proof predicated on this definition, then I need to have somewhere like an operating table. So writing a proof is a bit like doing surgery or something. Or, I don't know, maybe surgery is not the right metaphor. Maybe it is. But we have kind of this table, this arena. Maybe it's a stage, right? And we begin every proof with an empty stage. So we have no objects to work with. We have nothing. And so writing a proof is about casting the characters and then giving them something to do, right? And if I'm going to use this definition in service of a proof, the first thing that I would do is I would have to look at the first part of this definition. If I'm trying to prove that a set is dense, I'm going to try and prove that this definition holds. And so the first thing I would do is introduce the reader to elements A and B. And that brings A and B onto the stage. And it also tells us something about them. It tells me that A is a real number and that B is a real number, right? And so now having an A and B on the stage and knowing that they're real numbers, that lets us do a lot of stuff with A and B. We can do arithmetic with them. We can make assertions about decimal expansions if we know something about them. We can make assertions about whether it's rational or irrational using other things that we might know. So it gives us a lot of tools to bring A and B onto the stage and to decide that A and B are real numbers. And then the second part of this definition, if we were going to prove that this definition is true, now here's where the playwright has to do the most work, because we now have to introduce a new character, X, and X needs to belong to E, and also X has to satisfy the conclusion of this statement. And so then it's our job to figure out how to introduce an X that has both of those properties. X is in E, and X is between A and B. So this is getting at kind of what we were talking about a couple of class periods ago, that the form of your proof needs to mirror the logical form of the statement you're proving, right? And that's the skill I want for us to kind of hit over and over again today. Element that may still be missing is that in order for this inequality, A less than X less than B, to be even possibly satisfied, we should first know that A is less than B. Because otherwise, if we don't put that in there, I might choose an A and a B for which this definition is just not possible to be satisfied. Like if I choose A to be 7 and B to be 3, then I would be looking somehow for a number X which is greater than 7, but which is also less than 3. And there is no such element. So I agree, we should probably add that piece into our definition as well. And where would we put that? At what point do we need to tell the reader that A is less than B? Right in the first part. As soon as we introduce the reader to A and B, we need them to know that that is also something that must be satisfied. A less than B. Right? And so each of these elements, each of these components in this definition are important. So that, again, we all agree that we're speaking the same language about what density means, and also so that it helps us to structure out the proof. I want to make one more point about this definition using one other person's paper that I saw while I was walking around. Here's an alternate version of this definition that I saw on one of your papers. A set E is said to be dense in R if there exists an E, which is a real number, such that for all real numbers A and B, in the interval from A to B there contains a point E. So first of all, what do you notice about this definition as compared to the definition that we just finished amending? What's similar and what's not similar? So one thing that we see here is that there's a mixture of words and of logical symbols, which is okay. That's fine. I think having a logical symbols in at this point in the semester is helpful, so I'm glad to see that they're there because they'll help us to clarify our thinking when it comes to doing something with this definition. What else do you see that's either similar to the last definition we saw or maybe different? So we have a common element here from the last definition for all A and B, which are real numbers. This is also written as though the author here is not introducing us to two real numbers, A and B, but the author is actually introducing us to an interval, A and B, which works, actually, because that actually builds into the definition the fact that A is less than B. So here the author has gotten around the A less than B stipulation by introducing us to an interval instead of introducing us to two separate numbers, A and B. But given that that's happening, I would actually want to change something else about what's written here. I would want to change this symbol right there. How? Here the author has introduced us to not a number, which can be an element of the reals, but the author has introduced us to an interval, which is a subset of the reals. So what I would do here is I would trade out that element symbol for a subset containment symbol. So for all intervals A, B, which are subsets of the real numbers, and then the rest of it comes after that. Okay, what's another thing that you see that's different about the structure of this definition compared to the one that we saw previously? Other difference that on its face might not seem important, but it turns out is quite meaningful, is that here the author has introduced us to E before introducing us to A and B. So the order of the existential quantifier on the E and the universal quantifier on the A and B are reversed compared to our previous definition. Also, just to make sure that this aligns with our previous definition, this also needs to be an element of E, right? So again, compare. Our previous definition said something like for all A and B, and I'm going to make it an interval again here, just to align it exactly with what we're seeing here. So for all A and B reals, there exists an E in the set E such that A is less than E is less than B. So that was the previous definition. This definition just takes those two elements and it reverses their order. So for all A and B subset of the reals goes here, and there exists an element E of the set E goes there. So my question to you is, why is this a difference? Why is this a distinction with a difference? For a moment, I'd like for you to think about the difference between the two statements up here on the board, which aren't really statements about math, but rather about mathematicians, rather about all of you. So one statement says that for all students in our class, there exists a section of real analysis that they're enrolled in, that they're taking. That's statement number one. Statement number two, there exists a section of real analysis for all students in our class. So what I'd like to get us to think about is which one of these two statements are we more certain is true? Or which is the more accurate statement? Or maybe what is the difference between these two statements? Here's one way to think about it, and I want to do another example of this distinction after we get done talking about this example. But if I'm looking at the statement on the bottom, and I'm reading this statement, and I'm a proof writer trying to prove the statement on the bottom, here's my operating table, right? The stage, if you like, on which my players are going to play. What's the first thing that happens as I'm going to apply this definition to writing a proof? What's the first thing to which we get introduced? We get introduced to a section. And so on our stage, we have, and since it's an existential statement, we have one section that comes to the stage. There exists a section of Math 401. Great, so we put that section onto the stage. And then what does that section have to satisfy? All students belong to that section. So diagramming that out, what it's saying is that all students belong to that section. So that's what happens if we're trying to use the form of the statement on the bottom. Right? What about the form of the statement on the top? If I'm going to use that as a proof, if I'm going to use that as part of writing a proof, what's the first thing to which I get introduced up here?
students.
Right, I get introduced to for all students in our class, which means that the first thing that comes onto the stage in this play is an arbitrary student. So in the process of writing a proof, the first thing that we'll do is we'll have a student on the stage. Pick a student, any student, right? And then if we use this definition, what do we associate with that student? A section of Math 401. So in which of these scenarios is it possible for different students to have different sections? The top one or the bottom one? In the top scenario, every different student that I bring onto the stage could have a different section associated with them, right? Because the first thing that we're introduced to is an arbitrary student. And the first statement guarantees that that student will have a section. But different students are not precluded from having different sections. Whereas in the bottom example, the first thing that we're introduced to is one section. Maybe it's Math 401-001, the one that we're standing in right now, right? And then the assertion is that any student that I choose will belong to that section. So the one on the bottom guarantees that all students belong to the same section. The one on the top, that may be true, but it may not be true. So the statement on the bottom, in fact, is stronger. It implies the first statement, right? If it's true that there's one section with all real analysis students in it, then it also follows that every student will have a section of real analysis. But it's not necessarily true going the other way. I think an even simpler way to see this distinction may be to think about, just go to family relationships for a minute. And just think about the difference between the statement for all people, P, there exists a mother, biological mother, let's say, M, such that M is P's mom. Right? So there's one statement, but then what happens if I reverse the quantifiers? There exists a mother, M, such that for all people, P, M is P's mom. Which one of these two statements do we believe to be true? The top one, right? Because what would the bottom one imply? That there's one poor mom out there who is everybody's mother, right? I'm inclined to believe that's probably not true. Anyway, so that I think illustrates the importance that even though all of these elements in these two definitions are exactly the same, the order in which those two quantifiers appear makes a difference. Right? So it makes a difference whether the universal claim comes first and the existential claim second, or the existential claim comes first and the universal claim second. Let's try and illustrate why this example definition, again, same elements but different order. Here the existential quantifier comes first and the universal comes second. Let's see if we can illustrate why this is not a true statement. Why is it not true that there exists an E in E such that for all A and B that are subsets of the reals, the interval AB contains a point E? Let's write the proof that that is a false statement. And to prove that statement false, which statement do we need to prove true? So this is the other bit of this learning standard. We want to prove the negation of the standard of the statement down here on the bottom. And the negation of this statement would sound how? How would I write the negation of the statement that's down here on the bottom? What would it start with? Okay, so we want to prove that for all E belonging to the set E, and then what would come after that? There exists an AB, which is a subset of R, such that, and the conclusion of this definition was that AB contains a point E. So how would I finish its negation? We would negate that conclusion. AB doesn't contain E. Right? Okay, so moment we'll replace our E here with Q. Just to get a sense of why the statement in blue is actually a true statement. So is it true that for all rational numbers, we can find an interval of real numbers which doesn't contain that rational? How might we do that? If I want to prove that this statement is true, the first thing that I'll do, again, my proof should mirror the logical form of the statement. If I'm trying to prove this blue statement to be true, the first thing that appears is a universal quantifier. So what should I write? How do I mirror that in the first part of my proof? First thing we do in this play is we introduce the reader to an arbitrary rational number that we don't have control over because this is a universal claim, right? So the universe picks for us a rational number and we make peace with that. Let E be a rational number, and we may even be really brutal about it and say, let this E be arbitrarily chosen. Okay? So that's the first line in our proof. We introduce the reader to E, and now E is on our stage, right? And we know where E came from. It came from the rationals. So we have an E to work with, and E is a rational number. Okay, the next thing that we're going to need to do is produce for the reader an interval, AB, that satisfies this property. So let's quickly here take that last property, and let's kind of set that aside as the last thing that we're going to want in our proof. So our proof needs to end with the statement, thus, AB doesn't contain E. But looking ahead, that means that we're going to have to tell the reader what A and B are. And we only need one example. We only need to introduce them to a single A and B for which we can draw this conclusion. So what do you think? Now this is the creative part of the proof. If I've picked a rational number, E, how do I find an interval, AB, which doesn't contain that rational? What do you think? How can I construct an interval on the real line which doesn't contain E, for sure? Yeah. Right.
Both A and B are more than E.
Okay, so let's pick an A and let's pick a B which are more than E. So the picture that's emerging here is, yeah, we want to do that. Is there a way we can define the A and B constructively? Specifically? Because it only takes one example, right? So we don't have to be arbitrary about them being bigger than E. We can constructively guarantee that they're bigger than E. How do we do that? What's one way to do that?
Can you just make numbers up?
Well, since E isn't a specific number, we can't necessarily make a specific number up, but we could maybe make up an expression which is related to E.
Say like E plus 1.
How about that? So E plus 1 for A and maybe E plus 2 for B. And so at that stage, we are being the creators, right? Let's let A equal E plus 1 and B equal E plus 2. So now we've introduced the reader to two new players, A and B. And we've said what they are. A is E plus 1, B is E plus 2. How do we know that AB is a subset, the interval AB is a subset of the reals? Well, so this is a statement we're trying to prove here, right? So we don't know that this is true. We have a burden of proof to show that the A and the B that we've introduced them to also satisfy this piece. So how can we guarantee that the A and the B that we just wrote down are in fact real numbers? Yeah. Cool.
Would it be because E is in Q and Q is in R?
E is in Q and Q is in R. Yes, exactly. E is rational, and every rational is also real. So therefore, thus, since E is rational, and the rationals are a subset of the reals, okay, so that's the first thing we need to know. E is definitely real. So why is E plus 1 real? Yeah, in fact, E plus 1 is also rational. How do we know E plus 1 is rational? So that's one of our field axioms, right? That goes back to the axiomatic foundations of the rationals, right? E is rational, 1 is rational, and according to the field axioms, if I add two rational numbers together, I get another rational number. So E plus 1 is also rational, which is a subset of the reals. E plus 2 is also rational, and that's a subset of the reals, right? So all of that taken together is enough for us to say that A and B are definitely real numbers. Also, how do we know A is less than B? Using our order axioms from the first chapter, we can take the claim E plus 1 is less than E plus 2, which we're trying to justify, and we can subtract E from both sides. And if I subtract E from both sides, I get 1 and 2. And I think we can agree that 1 is less than 2. And therefore, E plus 1 is less than E plus 2. And then finally, why is E not an element of that interval? Because it's less than A. Well, because it's less than A. That's all we really need to say. Thus, AB doesn't contain the point E.